Hello friends, welcome to this video on the fundamentals of model analysis. In our study on the performance-based seismic design, we shall be again and again referring to the mode shapes, model vectors, etc. So I thought it would be nice to have a look of the fundamentals on the model analysis. Some terminologies related to the model analysis are like this. The mode shapes are the special distribution of masses in a vibrating system. Mode shape coefficients is the special distance of any mass from the neutral position. Mode shape vectors are vector arrangement of the mode shape coefficients. Modal mass is the apportionment of total mass that gets activated in a particular mode. Modal participation factor is the quantifier of the contribution of a particular mode in the overall vibration of the system. So this we shall be encountering again and again in our studies. Where from this mode shape comes? It comes from the free vibration analysis. Now we have taken the equation of motion here for multiple degree of freedom system with damping and an excitation function. Now if I remove the damping part and also remove the excitation part, then it becomes what is called free vibration. So the free vibration equation of motion is this: mu double dot plus ku equal to 0. This equation if you solve, you get the modal parameters like mode shape vectors, eigenvalues, or the frequencies of vibration. Let us consider a 3 degree of freedom system having masses m1, m2, m3 and the stiffnesses at different levels as k1, k2 and k3. It is usual and customary to represent any physical system to spring mass system or spring mass dashpot system. Since damping is not there, dashpot is not coming into picture. So we have taken spring mass system. This is the representation. Now this equation that we have seen in the previous slide is the equation of the free vibration, equation of motion for the free vibration. Now let us try to have a solution of the differential equation. For that purpose, we take a trial solution ut equal to a to the power minus lambda t phi. Here minus lambda t is used so that with time the vibration diminishes, and phi is a vector quantity of scalar coefficients, the mode shape coefficients. So this vector is the mode shape vector that we shall find out later on. So if we differentiate this trial solution, we get u dot equal to minus lambda a e to the power minus lambda t phi. Let me mention that the phi has been introduced to capture the spatial distribution of masses. Now we differentiate this a again, we get equation b u double dot t equal to lambda square a e to the power minus lambda t phi. Let us distribute this a and b, substitute in equation 2. Then what we get? We get this equation. Here e to the power minus lambda t is common in two terms, so it can be cancelled. Also it can be divided by lambda, and we get this equation m lambda phi minus k phi equal to a null vector. So this we can take together the two terms because lambda phi is a post multiplier. Phi is a post multiplier. So it can be taken on the right hand side. So we get m lambda minus k whole thing multiplied by phi equal to a null vector. This is equation 3. So for equation 3 to be valid, this determinant of the left hand side m lambda minus k of this matrix, the determinant should be 0. And this is actually an equation, a single equation, because right hand side is a scalar single value. This equation is called the characteristic equation. Solving this equation, you will be able to get the mode shape vectors and the eigenvalues or frequencies. Now equation 3 is written here once again for clarity, and we write it taking the negative side on the right hand side. So it will be lambda m phi equal to k phi. So if you remember, this is nothing but eigenvalue solution. The unknown vector phi is appearing in both sides of the equation, so this is what is called eigenvalue problem. There are several methods available for eigenvalue solution. One method we have discussed, the characteristic equation method. So when you solve this equation of this characteristic equation or this eigenvalue problem as given by equation 4, you get the all mode shape vectors and eigenvalues lambda, which can be converted to frequencies. How many eigenvectors will come out of the analysis? There will be as many eigenvectors and eigenvalues as the number of degrees of freedom of the vibrating system. Degrees of freedom, by the way, is the number of independent ways in which a structure can move. Let us take a 3-degree of freedom system. So the first mode shape vector is given by this. First mode shape vector, we are giving superscript 1 for the first mode, and the parameters here within the vector are phi 1, phi 2, phi 3 are the mode shape coefficients. So since it is a 3-degree freedom system, there are 3 mode shape coefficients in the first mode. Similarly, in the second mode, again there will be another new coefficients given with superscript 2, and the third mode shape vector. Now each mode shape is associated with a time period and a frequency. So we have the time period T1 associated with first mode and omega 1 associated with first mode. T and omega related through a simple equation, omega equal to twice pi by T. Similarly for second mode T2 and omega 2, and third mode T3 omega 3. Let us take a numerical example with numerical values. The problem I have already solved. The solution is not shown here. I am showing the final mode shape vectors. So first mode shape vectors are like this: 0.37, 0.73 and 1. Time period is 10.5 seconds, omega is 0.6 radian per second. This is hypothetically taken problem, that's why the time period is coming very large. Otherwise for a 3-degree of freedom system, such large time period will not come. Second mode shape vectors, first 2 coefficients are negative, third one is positive, and the time periods are lesser here now. The omega is higher because they are reciprocally related, T and omega, so T getting reduced, omega getting increased. For third mode, first mode shape coefficient is positive, second mode shape coefficient is negative, and third mode shape coefficient is again positive. So alternatively positive, negative you are getting in the third mode. Now the first mode, when it is a 3-degree of freedom system, we have 3 modes, and the first mode is the lowest mode or the fundamental mode, and the third mode is the highest mode. So what difference we see between these two? You see, for the first mode, all the coefficients, mode shape coefficients are positive, indicating all the masses are on the same side of the neutral position at any state of time. They can go also on the left hand side when they all will become negative of the same sign, either on the positive side or on the negative side, but all will be on the same side of the similar side of the neutral position. Second mode onwards there will be mixture, left, right, etc. But highest mode has another pattern. The pattern is one mass on the right hand side, next mass on the left hand side, next mass again on the right hand side, and so on alternatively. So all the masses here in the highest mode are out of phase. This is called what is called out of phase. And first mode, all the masses are in phase. These mode shape coefficients I have drawn to approximate scale, and it is looking like this. So first mode, you see all the masses are on the same side. It can be either on the right hand side or it can be on the left hand side of the neutral position of the building. Second mode, top mass on the right hand side, second 2 masses, bottom 2 masses are on the left hand side, or they can reverse as a mirror image. In the highest mode, top mass on the right hand side, but second mass on the left hand side, third mass on the right hand side again. So there all the masses are out of phase, either on the left or on the right. They maintain this out of phase condition. So looking at the mode shape, one will be able to say whether it is the highest mode or it is the first mode. To understand the mode shapes, we have taken another system which is a 4-degree of freedom system having masses m1 to m4. So the first mode shape is like this when all the masses are on the same side of the neutral position. Second mode shape, one mass is gone to the right, the other three masses are on the left hand side. Third mode, some out of phase is seen at the top and the next mass, but the bottom two masses are on the same side. Highest mode is the fourth mode because it is a 4-degree of freedom system. So here all the masses are out of phase. I think this will clarify what is mode shape and what does it mean. Now all the distances here of the masses from the neutral position are the mode shape coefficients. First mass, this is the distance, second mass, this is the distance, third mass we have shown here categorically. This is the phi 3, the mode shape coefficients for the third mass in the first mode. Now there is a term what is called the modal mass, very important term in dynamics. Now there is a orthogonality condition between any two non-identical modes. Something like that, their product is 0. You know, as if one vector is perpendicular to another, their product will be 0. So a similar situation arises here. We have taken the rth mode and the sth mode, two distinct separate modes, and we have taken their multiplication with mass in between. So it is phi r transpose m phi s is equal to a scalar 0. So this condition is called the orthogonality condition between modes. Any two non-identical modes will be following this condition. This condition utilized in the modal analysis extensively. Now if I substitute this S by R, then both the modes become R mode only and we get the condition like this. Phi R transpose M phi R, both the modes we have taken as Rth mode. Then it is not 0, as in the equation 5 it was 0. It is not 0 here but a scalar quantity which is called the modal mass for the rth mode. So this is the basic relationship and definition for the modal mass. But as we have seen in the second slide, the modal mass is that amount of mass which gets activated in that particular mode. When a system is vibrating dynamically, all the masses are not active, that is, they are not contributing. So in a particular mode, some masses will be activated, and in that very mode, in rth mode, the amount of mass that is activated will be given by this mr. Now what we have written here, phi r transpose m phi r equal to mr, is actually expanded form, is looking like this: phi 1, phi 2, phi 3 and so on up to phi n for the rth mode. And the mass matrix, here it is a diagonal matrix. A mass matrix will be diagonal when it is a lumped mass system, as it happens in the case of a stick model in building with lumped masses. At the different floors you have the masses m1, m2, m3. So off diagonal elements will be 0. This is a diagonal mass matrix, and again phi 1, phi 2, phi 3 rth mode. So if you multiply this, you get a scalar quantity mr, the modal mass for the rth mode. The modal mass can be obtained by the modal analysis. So if we take any mode, earlier we had taken rth mode, let us take kth mode, which is very common in different courses. So the modal mass for the kth mode mk is given by this expression, summation of wi phi I k whole thing square divided by g into summation of wi phi I k square. What are the parameters? Parameters are like this: n is the number of stories in the building, wi is the seismic weight of ith floor, phi I k is the mode shape coefficients for the ith floor in the kth mode. As we have seen earlier, in the 3-degree of freedom system or 4-degree of freedom system, there are mode shape coefficients starting from phi 1, phi 2, phi 3 and up to phi 4 for 4-degree of freedom system. So k is denoting that number, mode 1, mode 2, mode 3, and I is denoting the floor level, because at every floor level the mode shape coefficients are different. So phi I k is the mode shape coefficients for the ith floor for kth mode. So if we make the modal analysis, these phi I k values are known, and putting this you get the value of modal mass for the kth mode. Now there is another term, the participation factor. We have mode participation factor we have discussed in the beginning. This is the amount of contribution of a particular mode to the total vibration of the system. Every mode will not be contributing the same amount of, say, energy in the total vibration, and the contribution of each mode is quantified by this modal participation factor. It is given by this simple expression, summation of Wi phi ik divided by summation of Wi phi ik whole square. So pk is the mode participation factor for kth mode, and these values we have already discussed in the previous slide. So using this you can find out the participation factor. Now how many modes you will consider in the analysis? So different course will be giving you the prescription how many modes to be considered. I have taken the case of Indian code. The Indian code says as many modes to be considered which can represent at least 90% of the total mass. Let us take an example. Say total mass of a system is 93 kg. For mode 1 the modal mass m1 is 45 kg, say. For mode 2 it is 25 kg, for mode 3 it is 12 kg, and mode 4 5 kg. It is a 4 degree of freedom system. So total mass, if I take 4 modes only, no, it can be more degree of freedom. May say 10 degree of freedom system, I have taken only 4 modes. Okay, in the 4 modes, the sum of the modal mass is 87 kg, which is equal to 93% of the total mass. So as per Indian code, 90% has been represented. So for the purpose of analysis of this system having a n degree of freedom, I can go by taking only 4 mode shapes for the analysis. Now why not all n mode shapes? Because then the computation will be difficult, will be time taking and complex. So to avoid complexity and computational time, we want to reduce the number of modes to be considered in the analysis, and for design purpose this is the prescription for Indian code. Now there is a term called higher mode effects. As we have seen in the previous example, there was n number of modes, but we have considered only 4 modes. So we have left out n minus 4 number of modes in the analysis. This is going to accumulate some errors in the results, and if we discard those modes, then those errors will be higher if we discard more modes on the higher side. This is called the higher mode effects. If you can take all the modes together, then you will get 100% accuracy. But for the sake of computational effort reduction, we go for a limited number of modes, and the higher mode effects may be left out and may cause inaccuracy in your output results. In the previous case, only 93% mass was represented by 5 modes, so there was inaccuracy to the extent of 7%. And those 7% are higher mode effects. Now in the base share computation in different countries, the codes of different countries, there is equivalent static method available where the base share is given by this expression. This expression will be a little changing from country to country. I have taken the Indian case. So this is the seismicity level Z by 2, importance factor and response reduction factor R, and SFI is the spectral acceleration ratio corresponding to the time period T1 of the first mode. So you see obviously here in the computation of the base shear you are considering only one mode and only first mode. Though you are taking all the masses together, seismic weights you are taking together, but the vibration effect, the dynamic effect you are taking only for the first mode. So this will lead to some inaccuracy and higher mode effects will be left out. Now this can be overcome by considering the response spectrum method where many modes can be considered. But you cannot consider 100 number of modes in your analysis. For example, in SEP 2000 software, it considers only 12 modes in the beginning, 12 fundamental modes. So other modes will be left out, and suppose a building you are considering, multi-story building, there may be 20,000 nodes and 20,000 degrees of freedom, and there will be 20,000 eigenvectors, 20,000 eigenvalues, 20,000 frequencies. So I cannot take everything together, so there is a limit. I can take say 10, 12 or like that, depending on the accuracy I want. So in either method, the equilibratic method or response spectrum method, we cannot consider all the modes of the system. So some effects of the higher modes will be left out. Now there is an indirect way of considering this for building. How it is considered? Suppose the building is up to 10-story high, then the lateral force, the base shear you have computed, is distributed over the floors. Say ith floor will get Qi amount of lateral force. And this is given by this expression. Wi is the seismic weight of the ith floor, Hi is the height of the ith floor from the base of the building, and so on. So this is the summation of those Wj, Hi, Hj square. Now if it is 10-story building, the effect of higher modes may not be so high. But if it is more than 10-story, then the effect of higher mode effects will be considerable, and we apply a process here which has been of course established through research. We distribute only 90% of the base shear first. So 90% of the base shear is distributed as per the distribution formula of the relevant codes, and 10% of the base shear is left out. Now this distribution is done to all floors including the roof. So Qn indicates the roof lateral force. So roof lateral force is equal to the roof lateral force given by this expression plus the left out below of the base shear 0.1 Vb. So it has been established through research that with this process you can take the higher mode effects indirectly in the analysis and the results. Thank you very much. Please subscribe the channel, like and share the videos. Put your comments, if any, on the comment box. I will be glad to answer those questions to the extent of my capacity. Thank you.